In this video, we are going to look into an introduction to differential geometry. This video will contain all the essential aspects that are required to study differential geometry, starting from the basic concepts, definitions, manifolds, concepts, as well as the career objectives and prospects which lies when studying differential geometry. So this would be one single video containing all the important aspects of differential geometry, definition, applications, and so on. My name is Shaunak and you're watching this video on Physics for Students. I welcome you to my channel. So before we delve deep into the study of differential geometry, first let us look into what are the topics that we are covering. Here are the topics that we are covering. We will first start to understand differential geometry, how it is applicable to pure and applied mathematics, the usage of calculus in differential geometry, and a very important and fascinating journey into the history of differential geometry, the basic fundamental concepts like manifold and differential manifold, which includes tangent vectors, tangent bundles, what is smoothness and why do we need smoothness in differential geometry. We need to understand a little bit about diffeomorphism and invertible functions, and finally the most important aspect, what are the career prospects and jobs that lie in differential geometry. So here is a complete video which covers the most important aspects of differential geometry. So let us start and you will enjoy this fascinating journey. The first thing that we need to understand is that what is actually differential geometry. So if we start with the formal definition, then the first definition says differential geometry is a mathematical discipline that studies the geometry of smooth shapes and smooth spaces known as smooth manifolds. It also uses techniques like differential calculus, integral calculus, linear algebra, and multilinear algebra. So this definition of smooth shapes and smooth spaces we are going to cover later. So the second definition tells that differential geometry studies the geometry of curves, surfaces, and manifolds. And the third definition says a branch of differential geometry dealing with geometrical forms which studies with curves, surfaces, and mathematical analysis. Now these are the formal definitions of differential geometry in English literary language, but what is actually the meaning, let us find in the next part of this video. So when we talk of differential geometry, we are talking about studying of shapes, curves, objects in three-dimensional space. Also, we are using techniques such as calculus and linear algebra to study something which is called Riemann surface, and the study is invariant under a broad transformation, and it is used in general relativity, global positioning satellite, 3D modeling, and thermodynamics. So this is all in all what we can call is an overall idea about differential geometry. It is definitely a study of shapes, size, and objects, and it is used in 3 dimensions. And in order to measure those curvatures, we use calculus, linear algebra, and this study is invariant under a broad transformation so that calculation becomes easier under transformation of coordinates, and it is used in general relativity and other areas. But again, this is a very broad definition of differential geometry. What would be the exact pinpoint idea? Let us find it out in this part of the video. Okay, so when we talk of differential geometry, these type of shapes emerges into our mind. So you can see a cylinder, a manifold, and then different types of shapes which has got normals, parallelepiped, a sphere, all these things. So these are basically different, I would say, visualization of curvatures, manifolds, etc. Now the reason that I am showing you these type of different shapes, it will soon come to clear in the next part of the video. So first of all, when we talk of differential geometry, it is a branch of mathematics that studies curved surfaces. It uses differential calculus, mathematical analysis, and usually studied on a small scale. Now, when I talk of the last definition, studied on a small scale, I am trying to tell you that it is local, it is not global. So these are few of the simple definitions of differential geometry. Okay, so now we come to the basic core part, that differential geometry comprises of two words. First one differential and second one geometry. Now, whenever we are talking of this term differential, the first thing that comes to our mind is obviously calculus and differentiation, and geometry means study of shapes and sizes. So now we can understand that is the core idea of differential geometry is the study of shapes and sizes using calculus and differentiation. So now we can tell that we need to use calculus, differentiation and other methods to calculate the shapes and sizes of different geometrical objects. So starting from the basic few definitions and helping you to visualize those different types of manifolds and shapes, now we come to the central part of the definition, that is differential using differentiation and calculus, and geometry using measuring the shapes and sizes actually comprises of differential geometry. That means we are studying the geometry of shapes and sizes, but we are using calculus. The question is that why we are using calculus, we will find it soon. But before that, we need to find it out that differential geometry, how it is applicable and its branch in terms of applications and uses. So next, what we will try in this part of the video is that we will try to find out what are the different branches of differential geometry which are available and how it becomes useful for research and industry application. So if we take differential geometry as a whole, I mean to say broadly, then it is divided into two parts. The first part is a pure mathematical part. Now, when I talk of pure mathematics, it means that these things will be used for more of a research, not much directly into industry use. I will just give you a quick idea what do I mean by the pure mathematics of differential geometry, and I will just touch base on some of the important concepts. The first is Riemannian geometry, which studies Riemannian manifolds, smooth manifolds with Riemannian metric. So Riemannian geometry generalizes the normal school level Euclidean geometry to spaces that are not necessarily flat, though they still resemble Euclidean space at each point in finite symmetry. The second point is pseudo-Riemannian geometry, which again generalizes Riemannian geometry to the case in which the metric tensor need not to be positive definite. So I mean to say a special case of this is a Lorentzian manifold, which is the mathematical base of Einstein's general theory of gravity. The third, named after Paul Finsler, a German and Swiss mathematician, Finsler geometry has Finsler methods as main object of study. This is a differential manifold with a Finsler metric. Symplectic geometry is a study of symplectic manifolds. The word symplectic is an adjective which means placed in or among, as if woven together. Complex geometry is a study of geometric structures and constructions arising out or described by the complex numbers. Kähler geometry refers to the study of Kähler manifolds with three mutually compatible structures: one, a complex structure; two, a Riemannian structure; and third, a symplectic structure. Conformal geometry is the study of a set of angle preserving conformal transformation on space. These are the concepts, these are some of the topics of pure mathematical geometry. That means we can use them to make beautiful and different mathematical models. When I talk of the general relativity parts, the first one is tensors. Obviously, the entire Einstein's field equations and the basic root of general relativity are tensors. We deal with Riemann curvature tensor, which measures the curvature. We also deal with co- and contravariant tensors, that is the tensors which are varying in a smooth way or in an opposite direction. Then we have got metric tensor, which measures the causal structure of space-time. We also have got parallel transport, a way of measuring vectors movement along a surface, and geodesics, which are considered to be the shortest distance between 2 points. All these concepts of general relativity are being explained exclusively in my videos in the playlist General Relativity. So if you really want to look into it, you can go ahead and look into that. So these are the concepts and branches of differential geometry. However, we are now going more into understanding differential geometry in a much deeper way in the next part of the video. So when we talk of pure mathematics, Riemannian geometry, pseudo-Riemannian, etc., what it leads to, that it leads to, based on research and developing pure mathematical models, whereas the application based, which is tensors, metric tensor, parallel transport, geodesic, these are used mostly in industries like Google, artificial intelligence, deep learning, TensorFlow, Python, and so on. If you're really wondering that how tensors are used in Google or deep learning, you will just find out in a coming video of mine where I have shown how deep learning and tensor applications are intricately related with each other, and how the TensorFlow is related to the mathematical TensorFlow that we talk about. Okay, now that we have understood what is differential geometry, what are the applications, what most important is that why at all do we need to apply calculus and geometry? Now, when we talk of applying calculus or understanding that, we need to understand one simple concept which is called a manifold. Now, these are different shapes. Again, I have kept in order to make you visualize about what is a manifold. This is a very basic definition. Numerous different parts consisting of or operating of one unkind combined, having many different features and forms. It can also be called as a collection of points forming a certain kind of set, such as those of topologically closed surface, and so on. So these are the definitions which is basically meant by manifold. You can think it as sum having different forms and features and a collection of points who's composed of diverse elements. Soon we will come more into finding it out, but first, most importantly, we need to find out who really coined the term manifold. Now, I hope you understand this great mathematician, Bernhard Riemann. The term was first coined by this German mathematician, Bernhard Riemann, around 1854. It is this German term, manifold, and which means this, which I would not dare to pronounce because it would be wrong, which William Kingdon Clifford translated it as manifoldness. Now, in his Göttingen lecture, which was held in 1854, Riemann described the set of all possible of a variable with certain constraints, because a variable can have many values. It distinguishes between continuous manifoldness and discontinuous manifoldness depending on whether the value changes continuously or not. As continuous examples, Riemann referred not only to colors and the location of objects in space, but also the possible shapes of a spatial figure. So this was the inception of the concept of manifold in the opening Göttingen lecture of Riemann in 1854. Now, this is the famous book. It was this historical book where Riemann introduced the concept of manifold. As you can see, I have underlined in red, William Clifford translated this to English. The basic concept and ideas as well as their mathematical background are provided, putting Riemann's reasoning into the more general and systematic perspective achieved by later mathematician and physicist on the basis of his seminal ideas. It would be worthwhile just to mention one point, that when Riemann presented his ideas on a geometry in manifolds the first time to a scientific audience in his famous dissertation in 1854, he was completely aware that he was working in a border region between mathematics, physics, and philosophy, not only in the sense of the pragmatic reason that his audience was mixed, but by the very nature of his exposition. There was no linguistic or symbolical form inside mathematics. So this is some kind of a brief idea and a history on who coined the term, and this is the famous book where it is coined. So what we can do is that we can find out the simple definition of manifold is manifolds are objects in topological spaces where it deals with numerous shapes and forms that are bent, furled or wrapped, and every point of a manifold has a small area which looks like Euclidean. This is the most important form, that manifolds have objects which looks more like Euclidean. Okay, so why do we apply calculus? Let us find out the reason. If you see these shapes right on your screen, what you can understand that all of them have different corners which are highlighted in red. And because they have corners and because they are flat, we can say we can apply the postulates of Euclidean Cartesian geometry here. But what if they do not have corners and they look something like this? So these are the shapes which do not have any corners, and in order to find out any portion of the curvature, what we need to do is that we need to find out the derivatives. So finally, can we say something like this? So those shapes and sizes which looks like this, and these are the shapes which are discrete, and the corners, they have corners, so we can use methods of Euclidean geometry, whereas these type of shapes have no corners, they are continuous in nature, and we need to differentiate and hence use calculus to measure it. So now being said that why do we need calculus and geometry? The reason is that when we are trying to measure certain geometrical shapes which has got absolutely no corners, which are continuous in nature, we need to differentiate using calculus. So till now, I hope things are going pretty fine. We understood the meaning of differential geometry. We understood what is manifold. We also understood who coined the term manifold. And then we found out that this is the reason that we need to apply calculus and geometry. Till now, everything has been set. The goals have been achieved. But nothing would be complete until and unless we know a little bit of history of differential geometry. So sit back and enjoy with this fascinating journey on the inception of the concept of differential geometry. The study of differential geometry, or at least we can say the study of the geometry of smooth shapes, can be traced back at least to classical antiquity. In particular, much was known about the geometry of the earth to be a spherical geometry. In the time of the ancient Greek mathematicians, famously Eratosthenes calculated the circumference of the earth around 200 BC. Implicitly, throughout this time, principles that form the foundation of differential geometry and calculus were used in geodesy, although in a much more simplified form. Namely, as back as Euclid's Elements, it was understood that a straight line could be defined by its property by providing the shortest distance between 2 points, and applying this same principle to the surface of the earth leads to the conclusion of the great circles, which are only locally similar to straight lines in a flat plane, provide the shortest distance between 2 points on the earth's surface. The most significant development in the understanding of differential geometry came from Gerardus Mercator's development of what is called the Mercator projection as a way of mapping the earth. Mercator had an understanding of advantages and pitfalls of his map design, and in particular was aware of the conformal nature of his projection, as well as the difference between praga, the lines of shortest distance on the earth, and the direction, the straight line paths on his map. Mercator noted that the praga were oblique curvature in his projection. At this time, the recent work of René Descartes introducing analytic coordinates to geometry allowed geometric shapes of increasingly complexity to be described rigorously. In particular, around this time, Pierre de Fermat, Isaac Newton, Leibniz began the study of plane curves and the investigation of concepts such as points of inflection and circles of osculation with aid in the measurement of curvature. Shortly after this time, the Bernoulli brothers, Jacob and Johann Bernoulli, made early contributions to the use of infinite symbols to study geometry, and in lectures by Johann Bernoulli at that time, later collated by L'Hopital in his first textbook on differential calculus, the tangents to plane curves of various types are computed, and similarly points of inflections are calculated. In the wake of the development of analytic geometry of planes and curves, Alexis Clairaut began the study of space curves at just at the age of 16. Clairaut demonstrated an implicit understanding of tangent space of a surface and studied this idea using calculus for the first time. Importantly, Clairaut introduced the terminology of curvature and double curvature, essentially the notion of principal curvature later studied by Gauss and others. It was during this time this gentleman, Leonhard Euler, originally a student of Johann Bernoulli, made significant contribution not just the development of geometry but to mathematics more broadly. Euler studied the notion of a geodesic on a surface, deriving the first analytical geodesic equation, and later introduced the first set of intrinsic coordinate systems on a surface. Later in the 1700s, the French school led by Gaspard Monge began to make contributions to differential geometry. Monge made important contributions to the theory of plane curves and surfaces, and studied surfaces of revolution and envelopes of plane curves and space curves. Well, till now, these differential geometers and the history that we are understanding was much of a classical era, but we haven't got yet the breakthrough. And this breakthrough was made by this person, Nikolai Ivanovich Lobachevsky, a Russian mathematician and geometer known as for his primary work on hyperbolic geometry. William Kingdon Clifford, whose name we saw on the book of Riemann, called him as the Copernicus of geometry due to the revolutionary character of his work. Now, when he was just 7 years old, his father, a clerk in land surveying office, and Nikolai moved with his mother to Kazan. Nikolai attended Kazan Gymnasium from 1802 to 1807 and then received a scholarship at Kazan University. At Kazan University, Lobachevsky was influenced by Professor Johann Christian Martin Bartels, a former teacher and friend of German mathematician Carl Friedrich Gauss. Lobachevsky received a Master of Science in Physics and Mathematics in 1811, and in 1814 he became a lecturer at Kazan University, and in 1822, at the age of 30, he became a professor teaching mathematics, physics and astronomy. Now, Lobachevsky's main achievement is the development of non-Euclidean geometry, which is known as Lobachevskian geometry, and before him the mathematicians were trying to deduce Euclid's fifth postulate from other axioms. The non-Euclidean geometry that Lobachevsky developed is referred to as hyperbolic geometry, and this is where it triggered off the foundation of differential geometry. Some mathematicians and historians have wrongly claimed that Lobachevsky in his studies in non-Euclidean geometry was influenced by Gauss, which is not true. Gauss himself appreciated Lobachevsky's published works highly, but they never had personal correspondence between them prior to the publication. Although these three people, Gauss, Lobachevsky and Janusz Bolyai, can be credited with the discovery of hyperbolic geometry, Gauss never published his ideas, and Lobachevsky was the first to present his views to the world of the mathematical community. Now, this was during the era when Lobachevsky, Bolyai, Carl Gauss, they were deducing and finding out hyperbolic geometry. This restricts us to the classical era. But what we do now is called modern differential geometry. And this part of the video, we will be going through a wonderful journey to know some of the very important contributions in modern differential geometry. So the subject of modern differential geometry emerged out of early 1900 in response to the foundation contributions of many mathematicians, including Henri Poincaré on the foundation of topology. As a part of his broader movement, the notion of topological space was distilled by Felix Hausdorff. In 1914 to 1942, there were many different notions of manifold and combination of differential geometrical nature. L.E. Cartan reformulated the foundations of different geometry of smooth manifolds in terms of exterior calculus and the theory of moving planes, leading to what is called Einstein-Cartan theory. Following the early movements, many mathematicians contributed to the developments, including this person, Jean-Louis Cauzoul, who contributed connections in vector bundles. Xingchen Shern, who introduced characteristic classes to the subject and began to the study of complex manifolds, often considered to be the father of modern differential geometry. Xingtung Yao, a Chinese-American mathematician who was awarded the Fields Medal in 1982 in recognition of his contribution to partial differential equations, the Calavi conjecture, the positive energy theorem, and the Monge-Ampere equation. Yao is considered one of the major contributors to the development of modern differential geometry and geometric analysis. Sir William Valence Douglas Hodge expanded the understanding of differential forms, and Charles Ehresmann, who introduced the theory of fiber bundles and Ehresmann conductions, are very important. Among them, finally, we come to Sir Michael Francis Atiyah, who made significant contributions, including the Atiyah-Singer index theorem and the co-founder of topological K-theory. He was awarded the Fields Medal in 1966 and Abel Prize in 2004. So this is a kind of a brief journey starting from Eratosthenes ending up to Sir Michael Atiyah, a brief idea of the history of differential geometry, which I am sure that gives us a fairly better understanding of the subject. Okay, so now we come more into the fundamental concepts of differential geometry. Now, when we talk of fundamental concepts, it is a huge subject. It contains many parts, which is difficult to explain in one video. However, I have just summarized the fundamental concepts into few of the 4 or 5 parts. The first fundamental concept rotates around manifold, which is these Riemannian manifold, charts, immersion, etc. Then we come across what is called vector and tensor fields, which leads with Lie bracket, vector field, tensor product. The third would be bundles and connections, which is called fiber bundle. We just saw who discovered fiber bundle, vector bundle, and so on. And finally, the gauge theory, which comprises of the non-abelian gauge theory. So these are basically all in all what we consider the basic overall idea of geometry, but each particular subject requires a huge amount of time and details. However, we would be completing only the manifolds part in this part of the video and subsequently the others in the rest of the video part. So once we start talking about manifold, the first thing that we need to understand, or rather we would learn now, is that what is a differentiable manifold. So first we will understand from the basic definition. So you can read it out. Differential manifold is a type of manifold that is locally similar enough to apply calculus. It is a generalization to higher dimensional concept, and a differential manifold is a topological space which is locally homeomorphic to Euclidean space. So I'm not reading line by line, but you can take a pause and just take a note of what is differential manifold into. I'm just going more into explaining it in a visual manner. So if this is the surface of our sphere, or rather Earth, or whatever you consider, and this is I am standing right here, and I want to go from this point to this point, so I keep on moving from here to here, to here, and to here, and to here in different directions. Finally, we end up here. Okay. Now, if I want to plot the same sphere in a kind of a curve on a flat space or on a space which looks similar to local, I will draw this kind of a graph, right? And here also I will proceed in the same way from here to here, to here, to here, to here, and finally end up here. So what you can see is a kind of a similarity between the movement of this person from a sphere to a curved surface. And this is what locally resembles Euclidean space near each point. So this part, when I'm maybe in a space or somewhere else, I'm looking into the global aspect, and this is what is called local. So this is the first concept to understand differential manifold, that something which resembles a local Euclidean space is something which is called a differential manifold. So manifold space that is locally Euclidean we again take the sphere and we say this is a point P. So the neighboring points can be specified using x1, x2 variable up to xn. So Euclidean or Cartesian space is a space which comprises of x1, x2 up to going up to the real number Rn, and a local Euclidean space is a topological space which looks like Rn. So this one where the neighboring points are local, whereas this one will be Euclidean. So this is the basic concept of differential manifold. So if you take a kind of a sphere and a cylinder and a hyperboloid or something like this, then we draw lines. These are converging geodesics on straight lines. We call it just a positive curvature. Here the lines are parallel, so we call it zero curvature. And here the lines somehow are diverting. We call it negative curvature. Now, taken this kind of a manifold, if you're still plotting it in this kind of a black surface, which is the curvature, we will differentiate and differentiate into small pieces using calculus, and hence the area is called dA. And what we have done is that we have applied the rule of calculus of manifold from this curved surface onto those manifolds. So we can see that these yellow points which are emerging looks like an ordinary Euclidean space. So this is the basic concept that whatever the lines etc. we are drawing on a manifold, that should look locally like an Euclidean space, and because it is locally Euclidean, we can use calculus to do that. So here is a better kind of a visualization. These yellow boxes which we have differentiated emerges into Rn, and this we can say that this sign actually shows isomorphism. So manifold is a space that is locally isomorphic to Cartesian space. So on this kind of a space, these are the the lines marked in black. That means here we can perform differential calculus. So a differential or differentiable manifold is a topological manifold which has differentiable structure. These differentiable structure can be told of a differentiable structure on a set M makes into an n-dimensional differentiable manifold on which we can perform differential calculus. So this comprises or gives us a fairly clear idea of what is a differentiable manifold. We have already seen what is a manifold. This is a much more detailed what is a differentiable manifold. However, differentiable manifold also has got two important concepts which we are covering in this part of the video. These are called tangent vectors and tangent bundle. So in loosely we can say that if this is a curved surface and these are the this is the point and we draw tangent vectors. So roughly speaking, a tangent vector is an infinitesimal displacement at a specific point on a manifold. So if a circle is given, we draw a tangent vector. These are the different tangent vectors. So a tangent vector is a vector that is tangent to a curve or a surface at a given point. And because general relativity deals with a lot of curvatures, so tangent vectors are pretty important. So we understood that what is a differentiable manifold, we understood what is a tangent vectors. Now if we put all those tangent vectors or tangent bundle in one small space, say for example this is a curved space, right, and this is M, okay, and then we put up, this is a differentiable manifold. Now we understand what is a differential manifold. These orange arrows are all vectors, and now we put them in a bundle. So a tangent bundle on a differential manifold is the one which collects or assembles all the tangent vectors, right? So we understood what is a tangent bundle. We also understood what is a tangent vector, and we can understand that these vectors, all of them assemble in a place which is called tangent bundle. Now when we talk of tangent vector, tangent bundle, differential manifold, we have ignored till now one important concept which we are covering in the next part of the video, which is called smoothness. And most of the definitions in differential geometry, you will come across this concept, what is smoothness. So what we can say is that in mathematical analysis, the smoothness of a function is a property measured by the number of continuous derivatives it has over some domain. So a surface is smooth if it is locally homeomorphic to an Euclidean plane. So let us take this one, this global which we have seen, which locally resembles Euclidean space, and these lines, these blue ones, we can say that they lie on Rn, right? And this is isomorphic. So we can say that what is homeomorphic? This is a new term. So if there is a function f which is continuous, then its inverse will also be continuous. Let me show you on a demonstration. Say for example, this torus slowly turns into a cup, right? And then the cup again dissolves into what is a torus. So if f is the torus which has got a function, then as it goes to inverse, that it moves into curve, that is called homeomorphic. Again the cup, if it is straight, then it curves into an inverse function which is also a torus. So that means we can say that the cup and the torus are homeomorphic to each other. So a function could be considered smooth if it is a differentiable everywhere, and it is said to be infinitely differentiable, which we are going to see in the next part of the video. So what is smoothness? A surface is smooth if it is locally homeomorphic. What is homeomorphism? If there is a function f like a torus, it goes into a cup, and if it is a cup which is a function, it again moves into a torus. That means the function and its inverse both are true. So here we see that smoothness is a property which is measured by the number of continuous derivatives. So continuous derivatives means the function is differentiable and its derivatives are also a continuous function. So if f is differentiable, f prime x0 is continuous. So this is a differentiable function and it goes on and on, but this is a non-continuous function. So considering this to be a differentiable manifold and these are differentiated, we can call this to be a differentiable structure, and this part is a continuous derivative. That means we can continuously keep on getting the derivatives, and this part will also be a continuous function. We will see one more demonstration with that. So continuous derivatives have two parts. One, that it should be differentiable and it should be continuous. What do I mean by this? Look into this kind of a graph. These are non-differentiable functions. Obviously. Why? Because this is not continuous. But this one, this is smooth. It is smooth. And we call what is smoothness is locally Euclidean, but it is not differentiable because this red line shows that there is a gap. So what we can say is that a smoothness or smooth surface should be locally homeomorphic. We have seen that. Should have continuous derivatives over some domain. So SF is infinitely differentiable. It continues into what is called a C infinity function, which we will look up later. And it is allowed to differentiate as many times as we wish. So fx equal to sin x, if we differentiate and differentiate and differentiate, it will continue till infinity. So this is one very important concept of smoothness. That means if I take a surface like this one, it will be continuously differentiable. It will continue till infinity. Now the concept of smoothness, we understand that it should be continuously differentiable and the derivative should also be differentiable. It will go up to infinity. But the question is that why do we at all need smoothness? So here lies the answer. So if we get a kind of an xy and here we draw a kind of a graph and we get 2 points A and B, and if we are zooming this point into here, then what will happen is that if you take a derivative, first order derivative, second, third and so on, that means these 2 points, if it is plotted on a differentiable manifold, it will continue differentiating infinite. So this one, as you see on the globe, which is mapped from U to V into Rn, it continuously goes on differentiating. It becomes easy because it is easy to calculate. It is easy because we are avoiding bumps and jitters, and it helps us to map also a neighborhood, which is a part of topology. I'm not going to cover it right now. So a very simple example, you see the coffee beans had been differentiated first, and then on the second time we get a liquid coffee. So that means if we continuously differentiate it, then finally it will go into infinity. But the question is that what happens if the surface is not smooth? However, we are not considering this in this part of the video. So can we summarize something like this? Until we differentiate infinitely, obviously we do not get a smooth surface. If we get a smooth surface, it helps us to study surface easily. And infinite differentiation makes a smooth manifold, and it looks something which is in Euclidean space, and always Euclidean space are easy for us to calculate. So it is hierarchical. We need to differentiate infinitely. Then we get a surface which is easy to study, and it helps to get a smooth manifold and which looks like some Euclidean space. So we come to a very important concept of differential geometry, what is called diffeomorphism. So in general, the definition of diffeomorphism is that it is a homeomorphism. I mean to say, if we divide these two words, it looks like differential homeomorphism. So obviously it is a homeomorphism which preserves the differentiable structure on a manifold. In mathematics, also diffeomorphism is an isomorphism of smooth manifolds, and it is an invertible function that maps one differentiable manifold to another such that both the function and its inverse are differentiable. Don't worry about those lines. We will soon see it on a kind of a graph which will become easier. So the most important part is that diffeomorphism is something which preserves the differentiable structure. It should have an invertible function and it maps to one another. So we will concentrate on these three key points from the definition. Okay, so now you see this part on the left hand side is a rectangle, okay, or we can call it as a four-cycle. Now the right one is also a rectangle, this one, but it is twisted, okay. So in the sense of connectedness, these both graphs are structurally the same. But how we say this mathematically? We begin by introducing a notation for connectedness, or we can say adjacency, and we write using this symbol, which looks somewhat like isomorphism or equal, but we will call it as connectedness. For the fact that the nodes V1 and V2 marked in blue are connected by an edge. On the other hand, this one and this one is not. That is, this and this blue one. V1 is not connected, or you can say not equals to or not isomorphic to V3. Now we want to say that these both graphs are the same. So we can show this by giving way how to transform the left graph into the right one. This can be done by stating which vertex on the left should be mapped to which vertex on the right. We do this via a map which is called F. For example, we can say F of Vi equals to Wi. However, this specific transformation is not structure preserving in the following sense, that V1 is connected to V4, but V1 is not connected to the function of V4. So here you see W1 and W2. Now, just mapping each vertex with the index I on the left to its corresponds vertex with index I on the right will not give us transformation that demonstrates the equality of the graphs. So we see from this video that we need to claim for the map Vi, which is connected to Vj, implies that f of Vi is also connected to f of Vj for homeomorphism. Let us take an example following a valid structure preserving map for this graph. So you can see many different nodes can be mapped to the same node. This one, V1 goes to W1, V3 goes to W1, V2 goes to W3, and V3 goes to W3, right? So many different nodes can be mapped on the same node as long as they are not connected. Why? Because a node can, in this kind of graphs, never be connected by itself. So we obey the homeomorphism rule, and so what we actually found here is that the right subgraph consisting of the vertex W1 and W2 is somehow structurally similar to the complete left graph, and hence from here it follows that W1 is connected to W3, and hence we can say it implies that V1 is also connected to V3. So this is something which is called how we can preserve the structure. Okay, now we come to another important concept, what is an invertible function. If you remember, I just showed you the cup and the torus, one turning into another. So inverse functions are functions that reverse each other. So f and f inverse of 1. So a takes the input, goes into f, returns b, and b takes the input, and again it reverts back to a. So this is a kind of a demonstration of invert function. So it is an invertible function that maps one differential manifold to another such that both the function and its inverse are differentiable. So this one goes to this, and this one also comes back to this. It's a pretty simple example of an invertible function. Now the question is that can we use the invertible function in diffeomorphism? Because if you go back to the original definition of diffeomorphism, when we started what is diffeomorphism, you see that we actually talked about the invertible function also in the original definition. So a diffeomorphism we can call is in a sense an extension of the notion of homeomorphism. So a homeomorphism is simply a continuous function between topological spaces that has a continuous inverse. So this one, for example, a circle and an ellipse are diffeomorphism, right? Because we can deform a circle by smashing it into an ellipse, and we can say it also has an invertible function. So for example, this is a circle and this is a triangle. It is not diffeomorphic. So a circle and an ellipse are, can be diffeomorphic, but circle and a triangle is not. For example, this cup or a mug and a torus, it would be homeomorphic, but however it is not diffeomorphic. So what I'm trying to tell you is that homeomorphism, we can smoothen, sharpen edges. With diffeomorphism we cannot. So considering this mug and a torus, they are homeomorphic but not diffeomorphic. Why? Because the handle of the mug normally cannot be glued differentiably. Onto the safe side, a cube and a sphere are homeomorphic, but however they are not diffeomorphic. So what we can tell is that if we take this kind of a structure M and N given two manifolds, a differentiable map F is called diffeomorphism if it is a bijection and its inverse is differentiable. Obviously, it should be bijection and its inverse should be differentiable. So these two M and N are diffeomorphic, and it is denoted by this. If the function, say for example, S times continuously is differentiable, F is called C of S, which is called diffeomorphism. And finally we come to the conclusion that diffeomorphism is also an isomorphism of smooth manifolds. So this is another very important concept of mapping, inverse, etc. So given that till now we have been going more into the technical details, understanding manifolds, but now given all this knowledge together, we now need to find out that at all where we can use differential geometry and get a kind of a secure job. So before we go, let us summarize diffeomorphism. It is a structure preserving. How we maintain the structure, it is mentioned over there. It is a differentiable structure also. It is an invertible function, we have seen this, and mapping one differential manifold to another. We're using this kind of a chart. So that actually comprises or completes the understanding of diffeomorphism, and now it is the time that we go deep into the industry and find out what are the career prospects. Okay, so first is that obviously it helps a lot into electromagnetism. Second, it helps in robotics to study the control of linear system. You can also look into quantum field theory. Economics uses econometrics. Chemistry and biophysics uses modeling of cell membrane. Engineering using digital signal processing. Probability, various structures of Riemannian manifold. It is also used in structural geology, and the famous Grigori Perelman used differential geometry and Ricci flow to prove the Poincare conjecture. Now these are the applications of differential geometry. Let us find out the job path. These are the jobs. So you can go as a senior manager, analytic and insights. You can go as a data science, stress analysis, engineering, architecture, design, and data modeling. So what I'm trying to tell is that anything which relates to the structure of geometry, anything which deals with differentiation, structures, modeling, data, huge amount of data handling, these would be the jobs. And I can tell you with a lot of confidence that differential geometry has got a huge amount of industry applications. And by knowing that, you secure a very prestigious job in the society. So it's summary time. So let us find what we learned. We learned the overview, the different branches of differential geometry, the application. We also learned a fascinating history of modern and ancient differential geometry, the fundamental concepts of manifold, differential and manifold, tangent vectors, bundles, the concept of smoothness, why do we need smoothness, diffeomorphism, and how invertible functions results into diffeomorphism, and the job prospects in differential geometry. So this completes today's video on learning differential geometry. I hope you liked it. Please do like, comment, and put up your comments in the comment section of the video, and do press the bell icon to get all the notification from Physics for Students. We'll be promising you to come up with another interesting video on differential geometry, but till then, goodbye. This is Shaunak signing off from Physics for Students, wishing you a great weekend ahead.
Now, you can be a part of our team. You can send your scientific articles, essays, research papers, lesson plans on a particular subject of science. For further details, please write to us at editor@physicsforstudents.com. Stay safe and happy.